Hey guys, we're on the second question of the 2016 FRQ. There are some parts to this question that will not be on the 2020 exam. I'll go over those when we get to them. Just an overview of the question. We've got a reaction between this ionic salt and acidic solution that produces a basic solution with water and a gas. First part of the question, they want to know what type of reaction it is. Then they want you to identify the limiting reactant, talk about reaction rates. And then we're going to get D is what's not going to be included on the exam. But I'm going to go over that just because we've covered most of it. We just haven't done, like this first part, you could probably figure it out. The second part, the justify, we have not gotten to, but it's not too difficult. So the first part of the reaction is the identification part. So I'm going to start with the precipitation just because that's the easiest to eliminate or figure out. We've got a salt, a solid salt that dissolves in an acidic solution. We still have a ionic solution with water as a liquid and a gas. So no solid is formed in this reaction. So I can say that we don't have a precipitation reaction. Okay, so now we're going to go on to the redox because that's a little bit difficult. I'm going to teach you a trick here. I've got this, the acetate ion, that does not change from reactant to product. So none of those oxidation numbers change. That's a +1, that's a +1, they're not going to change. There's a +1, okay? Here, so we just want to look at this carbon atom and see if the oxidation numbers change from there to there. If that's a +1, that's a +1, the total of this is going to be -6. That must be a +4. So if we look at carbon over here, that's still a +4 because the oxygen is a -4. So it's not a redox reaction. Which means it must be an acid-base reaction. And let's take a look at why that is. This is an acid, okay? So here I've got an ionic salt, and it's going to dissolve into this. But remember, salts can be both neutral, acidic, and basic. If I look at this ion, that comes from a strong base. So this must be a basic salt. So that gives me, so this is going to donate a proton. That is going to pick up the proton. So we do have an acid-base reaction. Okay, limiting reactant. So let's take a look at what we have for our reactants. I've got that much of my solid, and I've got 60 milliliters of that solution. So let's start with our solid. I've got 2.24 grams of HCO3. I'm going to divide that by the molar mass, which is 84 grams. And that gives me 267 moles. Okay. For my other reactant, start with what you know. I've got 60 milliliters. I know the molarity is always in liters, so I'm going to convert that to liters, and it's 0.875 moles. Oops, sorry, moles of acetic acid. So that gives you 0.0525 moles. Okay, if I look up here, I have a 1-to-1 ratio. So you're just going to look for the least amount of moles, which is that. So that one is your limiting reactant. Okay, that's your limiting reactant. Next part of the question is a reaction rate. They want to know, they observe that the bubbling is rapid at the beginning and gradually slows as a reaction. They want you to explain this in terms of collisions. So make sure you talk about collisions between reactant particles in this answer. And I'm not going to write anything out here. I'm just going to explain that. But as your reactants start to produce product, the concentration of these are going to go down. Concentration of that's going to go up. So you're going to have less reactants to collide with one another. The collisions are going to become less likely, so the production of product is going to slow down. Okay, now we're getting into the part of the problem that's not going to be included on this year's exam. But we are going to go over it just because I think you can understand this. So in thermodynamic terms, so here they want to know, they're saying a reaction can be driven by enthalpy, which is your H, entropy, which is your which is S, or both. Okay, so in thermodynamic terms, they're talking about Gibbs free energy, and they want to know why is it spontaneous. Okay, so they're telling you that the flask gets cooler. If the flask gets cooler, the reaction is pulling energy from the environment, which means that this must be endothermic. Okay, and what we know about endothermic in terms of enthalpy is that requires energy. It's not going to be spontaneous if it requires energy. So that must not be driving the reaction. That's not providing the spontaneity to this reaction. In terms of entropy, we're looking at more disorder. So we're starting with a solid, we're starting with something in solution. We still have something in solution. We're producing a liquid, but we're producing a gas. So the entropy must be going up, which is preferable. Nature prefers that. So I would say that entropy is driving this reaction in terms of spontaneity. So the second part of this, they want to justify, and here's where you get into the math. Justify your selection in part D in terms of delta G. So that's your Gibbs free energy. So the formula that you're going to use here is your delta G is equal to your change in enthalpy naught minus temperature times the change in delta S. You want delta G to be negative. That makes it spontaneous. Okay. We know that if we have to add energy, and our chaos, if our entropy is decreasing, neither of those help to make this a negative process. So that is never going to be spontaneous. If I'm releasing energy and I'm becoming more chaotic, I don't like to use that term, that is always going to be spontaneous. In our situation, we've got, this is endothermic, so I have to add this. And this is also becoming, I'm increasing my entropy. So when you get this, it's going to be driven by temperature. You want the temperature, you want this to be a larger value, you want this to be a larger value than this. So if I'm increasing my entropy much more than this, that's going to make it more negative. So it's going to be temperature dependent. So that's how you would explain this. If they were both negative, again, it would be temperature dependent. This value would have to be much larger than this value for it to be spontaneous. All right, I think this is the last part of the problem, and now we're getting into molecular structure. They're saying that this has 3 carbon to oxygen bonds. 2 of them have the same length, and 1 bond is longer than the other 2. So they're telling you that the hydrogen is bonded to an oxygen, and you've got 3 oxygen bonds to carbon, okay? So if I look at this, there's only 3 bonds, 2, 4, 6, so I'm going to have to make one of these a double bond. And I get this structure. Okay. If I look at this, none of these bond angles are going to be the same. And I need 2 of them to be the same, which means this double bond must have some resonance between these 2. In other words, it's not stagnant between this oxygen, it's between both oxygens, which would make these bonds shorter than this bond. So this is a resonance structure. So to show that, you would have to draw both possibilities. So the double bond could not just be on that one, it could also be on the other oxygen. Okay, so in the box below, draw a Lewis dot diagram or diagrams. So you would just draw these resonance structures and that would suffice. Okay, I think this is the last part of the problem. But we've got here they're saying student prepares a solution with equal amounts of my acid and my basic salt. I've got a buffer. This would not be included on the exam, but we've gone over it, so let's talk about it. They're saying the pH of the solution is measured to be 4.7. Student adds 2 drops, not a whole lot, of a 3 molar nitric acid, strong acid, stirs a sample, and the pH doesn't change, which is the idea of a buffer. So they want to write a balanced net ionic equation for the reaction between that and the chemical species that is responsible. So I know I'm starting with that. That's my acid. So I've got to look at my buffer and see which is my base. That's an acid. That's going to be my base. Okay? So I know that it's going to react with the basic part of my buffer. But they're asking me to do a net ionic. So I've got to get rid of any spectator ions. In other words, those things that are totally soluble and remain in solution. So the net ionic would be that hydrogen ion reacting with the acetate ion to form my acetic acid. Okay, you could also change this to H3O plus. You could do it that way. But that would be the net ionic of that reaction.